this video, we will start the spectral analysis of angle modulations. The first comment is that this analysis is in general difficult, and it is difficult because of the nonlinear relationship between the information that we want to transmit, the modulating signal m of t, and the signal that is transmitted, the modulated signal s of t. And the phase term phi of t, where we include the modulating signal, is proportional to this signal for a phase modulation, and it is proportional to the integral of the modulating signal in a frequency modulation. But in any case, this term is inside of the argument of a sinusoidal carrier, and therefore we have a nonlinear relationship between m of t and s of t. And this makes difficult the analytical study of these kind of modulations. It is also only possible to obtain results in very simple cases: narrow band angle modulations with sinusoidal modulating signals, and angle modulations with periodic modulating signals. In the general case, it's only possible to use heuristic rules. In this case, the most common one is the Carson's rules, to get an approximation of the bandwidth. Now we are going to analyze one of the few cases that can be studied analytically: the case of a narrow band angle modulation. An angle modulation is narrow band when the phase term phi of t is much lower than 1. This means that the phase or frequency deviation constants, or the modulation index, are small in this case. And for narrow band angle modulations, the spectral analysis is relatively simple. This is the expression of the modulated signal in an angle modulation, and if we use just a single trigonometric relationship for the cosine of the addition of two terms, and then we approximate cosine of a small number as 1 and sine of a small number as the number itself, it's straightforward to obtain first this expression using the approximation of the cosine of the addition of two terms, and then this is approximated to 1 and this is approximated by phi of t. And in this case, we obtain this approximated expression for the modulating signal s of t. AC cosine, this is the carrier, and then the term phi of t is multiplied by a sine in this second term. This expression is relatively similar to the modulated signal for an amplitude modulation, because here we have a minus sign, here we have a positive one, but here we have a sine, here we have a cosine. There is only a difference of 90 degrees, and the expression is relatively similar. Taking into account the similarity, the spectrum is also similar. We have the spectrum of the first term, a carrier, and the spectrum is 2 deltas, and then we have the spectrum of something that contains the message phi of t times a sinusoidal carrier, similarly to what we have here. And this term has a frequency response that is basically given by two replicas of the spectrum of, in this case, phi of t shifted to minus omega c and to plus omega c. If now we take into account the expressions for phi in a phase modulation and in a frequency modulation, the replicas that we have in plus and minus omega c are replicas of the frequency response of the modulating signal in a phase modulation and replicas of the frequency response of the integral of the modulating signal in the frequency domain, division by j omega in the case of a frequency modulation. In any case, as in the conventional amplitude modulation, the bandwidth is approximately equal to 2 times the bandwidth of the modulating signal, because the replica will produce a bandwidth 2 times W when it is shifted to plus and minus omega c, and the support for the for the frequency response of the integral is the support of the spectrum of the modulating signal, which has also a bandwidth 2 times the bandwidth of the modulating signal when it is shifted to plus omega c. As a summary, given the similarity with the amplitude modulation, is relatively simple to analyze the spectrum of a narrowband angle modulation. We have a carrier minus, in this case, something where we have the modulating signal. The modulating signal or the integral of the modulating signal for phase or frequency modulation times a sine, and the spectrum for a deterministic function or for a random function is given by a couple of deltas, the spectrum of the carrier, and then shifted replicas of the Fourier transform for deterministic signals or replicas of the power spectral density for random signals shifted to plus omega c and to minus omega c. And the spectrum that is shifted is the proportional to the spectrum of the modulating signal in a phase modulation and proportional to the spectrum of the integral of the modulating signal for the frequency modulation. In the frequency domain, the integral corresponds to a division by j omega. For a power spectral density, we have a square modulus of this.